Okay, so today I'm going to continue what we started discussing last Thursday. This is part 2A of the module on BJTs as amplifiers. So this is really introducing the BJT as an amplifier. If you have any questions while I'm doing the lecture, please either shout out please, I prefer you to shout out your question because I might not be able to see the chat box right away. So this is what I plan to cover today, amplifier basics. Then we're going to discuss a simple common emitter BJT amplifier. Then I'm going to give an introduction to biasing. If we still have time after that, I'm going to jump to the next topic, which is BJT biasing. So hopefully we will have a little bit of time to get into biasing. Okay, so let's start with amplification. Okay. What does amplification do? Amplification increases the power a signal can deliver while retaining all the information in the signal. So the premise here is that you have a signal, it's a weak signal. It will not be able to drive a substantial load. You want it to be able to drive a substantial load, so you have to increase the power the signal can deliver. And that's what an amplifier do. That's what amplification is. This is the symbol of an amplifier, a triangle. When you see a triangle, that's the symbol of an amplifier. If you remember the op-amp, the symbol of the op-amp is a triangle, although the op-amp is a two-input amplifier. Well, this is a more general symbol for an amplifier, single input, single output. So your premise is that you have a weak signal at the input and you want to strengthen the signal at the output. Let's say X is your input, Y is your output. Your output is equal to A times X. Y is equal to A times X, where we call A the gain. A is the gain of your amplifier. If the information at the input is not preserved at the output, then we say that the amplifier output is distorted. So what are signs of distortion? For example, if it's speech or if it's music, your speech might be garbled, or your music might sound wrong on or something like that. No? So that those are signs of distortion. All that means is that the information at the input was not preserved at the output. Okay. We usually describe amplifiers through their transfer characteristics. So what is transfer characteristic? No, that is a plot of the output versus the input. Okay. So transfer characteristics is a plot of the output versus the input. Let me give you an example. This is an example of your transfer characteristics where you're plotting Y, your output, versus X. Okay. It shows three regions of operation. You have a region where you reach a negative limit. Then you have a linear region of operation. And then you have a region where you reach a positive limit. The slope of this line, your linear operation, is A, which is your gain. So you remember the previous figure? Okay. A is used to describe the gain of the amplifier. Okay, does this look familiar to you? Anybody that can tell me where he or she has seen a similar plot before? Anyone? That's right, no? That's right, no? You saw that in the op-amp. Okay. Okay. Okay, so A has to be a constant if the system is going to be a linear system. In other words, A cannot be a variable, or A cannot vary with respect to the input. No, A has to be a constant. Okay? Now, X and Y don't have to be the same type of signal. Okay, so here are some examples. No? Remember, X is our input and Y is our output. When both the input and output are voltages, then we call this a voltage amplifier. And the gain is dimensionless. Your gain in a voltage amplifier is dimensionless. However, we usually just say volts per volt. So pag voltage amplifier, your gain is volts per volt. When the input is a current and the output is a current, okay, then that is a current amplifier. And A here is equal to amperes per ampere. Okay. When the input is a current and the output is a voltage, then you call that a trans resistance amplifier. Okay, a trans resistance amplifier. Now, what is your gain? Your gain will have units, converting current to voltage will have units ohms, right? When you multiply current by ohms, the output is voltage. On the other hand, when your input is a voltage, your output is current, you call that a transconductance amplifier, and your gain will be Siemens. Okay, sometimes you see instead of volts per volt, you see volts per millivolt. So that's also possible. All that means is how many volts per millivolt input. And you saw that when we described the operational amplifier. The open loop gain of an operational amplifier is expressed usually in terms of volts per millivolt. Okay, any questions so far? Any questions so far? No? Give me a sign if you have no question. No? So I also know whether you're still with me. Okay, thank you. Thank you to those that responded. Okay, this is a simple common emitter BJT amplifier. I think you've seen this before. You've seen this in EEE 123. This example was used to illustrate how the BJT is capable of amplifying input signals. So this is a simple of probably the most common amplifier, BJT amplifier you can have. So here is the circuit. Okay, consists of only three components: your transistor, no, a base resistance, and a collector resistance. The input is applied to the base through the base resistance, and the output is at the collector. And then you have these particular parameters. Okay, what I did here, which we did in EEE 123, was for different values of input, okay, we computed the corresponding values of output. For example, we know that when the input is equal to 0, then it is impossible for your base emitter junction to be forward biased, and therefore this transistor will be cut off. Cut off means no collector current, and therefore you will have no voltage drop across RC, and therefore V out will just be equal to VCC, which is what you see here. Okay. When your input is 0.7 volts, that is when your base emitter junction is on the verge of conducting. It is on the verge of conducting. Now, we're using here the constant current drop, constant voltage drop model of the base emitter junction. In other words, we're just approximating your base emitter voltage to be 0.7 volts when it is conducting. So that's the constant voltage drop model of your base emitter junction. So when that is 0.7, this is on the verge of conducting, but probably not quite conducting yet. And therefore, your collector current is still 0, and therefore your output voltage is still 5 volts. Now, what happens when your input voltage increases beyond 0.7? So now you have this conducting. Your base emitter junction is now conducting, and you will have a collector current. Therefore, you have a voltage drop across your collector resistor. Okay, so V out will be smaller now than VCC because of this voltage drop. No? So in this instance, it is going to be 4 volts. No? Now, I hope you still remember how to do these computations. These are the very basic computations for bipolar junction transistors. So first, what do you do? No? First, you compute for example, no? For this particular case, what do you do? First, you compute for IB. Right? What is IB? IB is simply V in minus VBE over RB. So V in is 0.8, VBE is 0.7. So V in minus VBE is 0.1, RB is 10K. No? So what you get is 10 microamperes. 10 microamperes. Okay? You multiply that by beta to get IC. So IC is equal to beta times IB. No? So 10 microamperes times 100 would give you 1 milliampere. No? So IC is equal to 1 milliampere. This is 1K. You're going to have a 1 volt drop here. And that's why VCC will drop from 5 volts to 4 volts. So that's what you see here. Okay. By the way, no, after you do these computations, you have to validate that this is still in active mode. How do we know that? Well, if V out is equal to 4 volts, that means VCE is equal to 4 volts. You know that it is in active mode if VCE is greater than VCE sat. So 4 volts is definitely greater than 0.2 volts. So we know that this is in active mode. And therefore, this equation, IC equal to beta IB, is valid. So we do that for all of these values, no? 0.8, 0.94. Why did I choose 0.94? I'm going to explain later on. No? This is a special value, 1.1, 1.15. And you're going to find out that at 1.18, no, exactly 1.18, your output is 0.2 volts. In other words, you are still in active mode, but now you're almost on the verge of saturation. Because the minute V out becomes less than or equal to VCE sat, then we know it is saturated, and therefore V out will just be, in our simplified model of the BJT, equal to VCE sat, which is 0.2 volts. So that's what happens here in these last two entries to this particular table. Okay, so before I continue, any questions with regard to this table? No? Are there any questions with regard to this table? Again, no? Please show me a sign that you're still with me. Okay. Okay, thank you. Okay, so what am I going to do next? No? What I'm going to do next is I'm going to plot this. No? I'm going to plot V out versus V in. No? Those are my transfer characteristics. Remember what we said? No? Your amplifier can be characterized by its transfer characteristics. This is a plot of your output versus your input. So I want to plot my output, which is a voltage, versus my input. So this is actually a voltage amplifier, if it indeed amplifies. And this is how your plot will look like. Note that when your input, V in, is anywhere from 0 all the way to 0.7, your transistor is just cut off, and the output is just equal to VCC, which is 5 volts. Okay. As soon as your input exceeds 0.7, your output will start linearly decreasing. Okay, so remember, no? Dito 0.8, it becomes 4. 0.94, it becomes 2.6. 1.1, it becomes 1. This is actually a linear decrease with V in. So it starts linearly decreasing. By how much or until when will it decrease? It will decrease when your output is now equal to the saturation voltage, VCE sat, which is 0.2 volts. At that point, it will not decrease any further. Your output will stay the same at VCE sat. Okay, so this is your transfer characteristic curve. How may we be able to make use of this curve? No? How can we make use of this curve? Okay, so this is your transfer characteristic curve. We see that it operates in active mode from here to here. No? So again, remember, no, this is cut off. This is cut off. This is active. And then this is saturated. So we see that it is in active mode from 0.7 to 1.18. Now that is when V in is 0.7 to 1.18. No? Now let's say we apply a sinusoidal voltage. So this is a voltage that varies with time. We apply a sinusoidal voltage at the input. What I'm going to do, I'm going to rotate the plot of V in versus time 90 degrees clockwise. So normally you would see this plot 90 degrees counterclockwise. So I rotated it 90 degrees clockwise so that I can plot, as my input varies, I can plot through this line what my output is going to look like. So what will my output look like? First, at this particular point in time, my output will be 2.6. Okay. When my input becomes its maximum peak value, my output will be 1.18. When my input is its minimum peak value, my output will be 5, VCC. Remember, this is VCC 5 volts. Okay, and so forth. So if I plot that versus time, this is what it will look like. Again, at this point in time, my output is 2.6. At this point in time, which corresponds to this point in time, so this corresponds to this, my output is 1.18. This point corresponds to this point, my output is 5, and so forth. So as my input varies this way, okay, my output is varying this way. My output is actually a negative of the input. If you're only taking a look at the time varying component of my signal, my output is actually a negative of the input. Okay. Now observe. The time varying component of my input that varies from 0.7 to 1.18, that is equal to 0.48 volts. From 0.7 to 1.18 is 0.48 volts. If I take a look at the time varying component of my output, okay, that is from 1.18 to 5 volts, okay, this distance from 5 volts all the way down to, sorry, not 1.18, 5 volts all the way down to 0.02 volts, is 4.8 volts. So the peak-to-peak value of my input is 0.48. The peak-to-peak value of my output is 4.8. So I have a gain. The magnitude of my gain is 10, but I put here a negative sign because when my input is increasing, my output is decreasing. In other words, my output, you might say that my output is 180 degrees out of phase with my input, or my output is the negative of my input. So my gain is negative 10. So you see that there is amplification. The voltage is magnified by 10, and therefore now this can drive, if it is going to be used to drive a load, it can drive a larger load. Any question? Any questions so far? Okay. Hopefully none. Okay, what happens if the peak-to-peak value of my input is increased? So remember here, my input is 0.48 volts peak-to-peak. Okay. What if I make it larger than that? So take a look at this input. It is greater than 0.48 volts peak-to-peak. Okay, what happens is, at this point, I already hit saturation. So from this point onward, my output will be constant at 0.2 volts. So that will be from this point all the way back to this point. My output will be constant at 0.2 volts. Now, when my voltage is decreasing, at this point, I hit cutoff. Okay, so from this point all the way to this point, my output will be constant at 5 volts. So this is what my output is going to look like. Okay. this is what it would have been. This is what it would have been, okay, if I did not hit saturation and cut off that early. But because I hit saturation and cut off, okay, before the signal could finish extending itself, okay, I have clipping here, negative clipping here at VCE SAT, and positive clipping here at VCC. So here, my output is clipped at VCE SAT, with this particular case 0.2 volts. And here, my output is clipped at VCC, which is 5 volts. Okay? So this is what happens. This is what happens. Okay, when your time varying component of your input signal is too large, there is clipping. So there is a maximum peak-to-peak value of your input signal that you can amplify without distortion, because, okay, this is now obviously a distorted output. You do not preserve, you are no longer preserving faithfully the information at the input when your output looks like this. Okay? The maximum peak-to-peak value of your input that can be amplified without distortion is only 0.48 volts. Okay, by the way, we call this 4.8 volts, we call this your maximum possible output voltage swing. The maximum possible output voltage swing. If your output voltage tries to become greater than this 4.8 volts peak to peak, then there's already distortion. So take note of the term, output voltage swing. Okay, what about the situation where, okay, remember here, your input signal is offset. No? It has a DC component and it has a time varying component. No? That's why we use, you remember, I hope you remember the okay, our standard for specifying signals that are like that. No? Okay, the subscript should be capital. No? When you have small v capital IN, that means that this is a time varying signal that consists of both a DC component and a time varying component. So your DC component is now 0.94, no? And your time varying component, well, I don't like this example, no? Example here, no? Your DC component is 0.94 and your time varying component is 0.48 volts peak to peak, no? Or if you want to express it in terms of amplitude, the amplitude is 0.24 volts. No? Amplitude is 0.24 volts. Peak to peak value is 0.48 volts. Okay. What happens, no? If the, okay, so this is still 0.48 volts. Earlier, we were able to amplify this properly without any distortion. What happens if I change, no, my DC component? What happens if I change my DC component? No? So for example, what if I shift or increase my DC component? So this DC component now is greater than the original 0.94 volts. What will happen now is on the positive cycle of my time varying input, I'm going to hit saturation right away. So at this point, dito pa lang sa point na to, I will already saturate. And I will be saturated from this point to this point. No? Now, fortunately, nothing's going to happen to the negative cycle, because during the negative cycle, I will still be in the linear region. So if I take a look at what my output will look like, it's going to look like this. So here, at this point, okay, I'm going to hit saturation. So my negative portion, the negative portion of my output will be clipped. No? Nothing is going to happen to the positive portion of my output. Okay, so if I do not want to have any distortion, what do I have to do? I have to reduce the amplitude of my input signal. if I do not want to have any distortion, what should my maximum input signal look like? No, my maximum input signal will only be something like this. No? Hindi dapat lumampas dito sa point na to. Okay, if your input signal is symmetrical, then that would also make the negative portion smaller. No? So that my output, okay, correspondingly, my output now will look something like this. No? Ganyan lang yung output ko. No? If I reduce my input, no? If I reduce my input, by the way, no? So this is the input, and then this is the corresponding output. Output. So what happened? The peak-to-peak value reduced. So the maximum possible output voltage swing without distortion got reduced because I shifted my signal to the right, no? Or I increased the DC component of my signal. Okay. In the same manner, if I decrease the DC component of my signal, no? Dito naman ako mag-clip, ano? Dito naman sa negative portion, no? It's going to look like this. No? Okay. So this pushes the transistor to cut off during the negative peaks. So again, it will clip here. So again, that reduces the peak-to-peak value of the signal that I can amplify. Okay. So what am I saying here? No? The choice of your DC component is very important. The choice of your DC component is very important because if you choose if you choose a good value for your DC component, that will maximize the peak-to-peak value of your input signal that you can amplify without distortion. Okay, I can show that in the form of a simple demo. No? So let me shift to another app here. Yeah. Let me start with this. No, let me start with this. Okay. Notice here. Notice. Sorry. Can you see my screen, everyone? I shifted app. Can you still see my screen? Okay, good. Okay. Notice here. I did not have no. To. I did not put any DC component in my input. No, my input is just a 1 kilohertz signal. In this particular case, its amplitude is 50 millivolts, no, or this is 100 millivolts peak to peak, no, 0.1 volts peak to peak. Okay, if you take a look at what that signal looks like, no, yeah, let's take a look at what that signal looks like. Okay, that's what the signal will look like. No, it's a sinusoidal voltage. Okay, which is from negative, well, from negative 50 millivolts to positive 50 millivolts. Okay. Will there be any useful output? What do you think? No? Will there be any useful output? The answer is going to be no. There's not going to be any useful output. Why? No? When my input signal is negative, obviously my base emitter junction will be reverse biased, and therefore my transistor will be cut off. On the other hand, when my input signal is positive, it only goes up to 50 millivolts. That is not enough. That is not enough to forward bias my base emitter junction. No? So obviously, I can enter this input signal at the base, but obviously it's not going to do anything. No? As a matter of fact, if I take a look at the output, okay, so now this is on a bigger scale. So you see my input is much smaller because hindi na natin makita yung 50 millivolts, ano? Because my output, which is the green line, is now 5 volts, right? Because my transistor is cut off all the time. So you might say, okay, why don't I increase the amplitude of my input? I can do that. I can increase the amplitude of my input. So right now it's 50 millivolts. Okay. 100 millivolts, still nothing. Okay. 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 It will start doing something, no? When my amplitude is greater than 0.7 volts. So you can see now here, you can see now the dips in my output, no? Because during the positive cycle, there's a certain portion now that my transistor starts to conduct. And as I further increase to, let's say, close to 0.7 volts, okay, now you can see that it's starting to conduct during the peak of my positive cycle. That's the only time my base emitter junction becomes forward biased. No? And then during the negative cycle, nothing happens because my base emitter junction is reverse biased. So again, you cannot amplify. No? There's no amplification here, and whatever your output is very distorted. It looks nothing like your input. Okay. Now let's take a look at the example that I just gave you earlier. No? So this is the example that I gave you earlier. Okay. If you take a look at this is a DC voltage, which is 0.94 volts. This is my input signal, which I gave an amplitude of 0.24 volts, no, or 0.48 volts peak to peak. It's 0.24 volts amplitude or 0.48 volts peak to peak. This is a transistor whose beta is equal to 100, although the simulator that I'm using uses a more advanced model of the transistor. 10K resistor, 1K ohm collector resistor, and a 5-volt supply. If I just take a look at my input, okay, if I just take a look at my input, okay, so it is offset. So notice it is offset by 0.94 volts. Okay, the minimum value is 0.7 volts. The maximum value is about 1.2 volts. Actually, it will be a little less than 1.2 volts. The peak-to-peak value will be 0.48 volts or 480 millivolts. No, if you can read the figures in the bar, okay, you can see there that the peak-to-peak value is 480 millivolts. Okay, and what I told you was these amplifiers. If I take a look at this signal, okay, you can see the amplification. So the first case that I gave you was, what if I made the peak-to-peak value of my input greater? Right now, it's 240 millivolts. If I make it, let's say, 300 millivolts, now you can see a little bit of distortion. The top and bottom parts are starting to flatten. I further increase, it further flattens. So you see that the output is no longer a replica of the input. Okay. So let's bring it back to, what was it earlier, 240? Yeah, let's bring it back to 240, which it was earlier, because this is the optimum that we saw. Okay. Now it's back to 240. What will happen if I just adjust my DC component? So right now it's 940 millivolts. Let me just make it 1 volt. Okay. So I adjusted it to make it 1 volt. Okay. You probably don't notice it, but at the bottom portion of your signal, you already have some distortion. It's not yet very noticeable, but there's already some distortion at the bottom portion. So let me just exaggerate it a bit. Okay. So now I made it 1.3 volts. So now you see that really the bottom portion is already gone, 1.3 volts. So that's how my signal now looks like when my input is 1.3 volts. Okay, the same thing happens when I reduce it. If I reduce it, it's the top portion that will clip. So now I reduced it to, let's say, 0.8 volts, and now you see the top portion that is clipping. Okay, so that just illustrates the different factors that I mentioned earlier with regard to setting up the DC component of your input signal with regard to the peak-to-peak value, maximum peak-to-peak value of your input signal that can be amplified without distortion, and with respect to the maximum output voltage range. Okay, so much for that. So let's go back to the presentation. Okay. So what are the observations that we can make from this? Okay, number one, the smaller the value of RB, the larger the gain. The smaller the value of RB, the larger the gain. Why is that so? Okay, we can go back to this circuit. The smaller the value of RB, the smaller the input voltage that is needed to produce the same base voltage. No? Again, no? The smaller the value of RB, the smaller the input voltage that is needed to produce the same base voltage, right? So you have we have the same V out, but a smaller V in. So obviously your gain, when we talk about gain here, we talk about magnitude, no? Because the gain is negative. So we're talking about the magnitude of the gain. So you have again, no? You have a smaller V in, the same IB, and therefore the same V out. Therefore, your gain is larger. So that's the first important observation. The smaller the value of RB, the larger the gain. Okay. In fact, the largest possible gain occurs when RB is equal to 0. The largest possible gain occurs when RB is equal to 0. When RB is equal to 0, we can no longer use the constant voltage drop model of our base emitter diode. Okay. If we use the constant voltage drop model of our base emitter diode, if this is silicon, we say that that is 0.7. If this is 0, then you will have an invalid circuit because you will have an input voltage that might be different from VBE, no? Which you assume to be 0.7. So you can no longer use that particular model. As a matter of fact, when RB is equal to 0, we have no choice. We now have to use Shockley's model. And this is actually what we're going to be doing when we do small signal analysis. Okay, so anyway, just imagine, no? The smaller the value of RB, the larger the gain. Maximum gain will occur when RB is equal to 0. Okay, then another observation. Notice that we had to place an offset voltage, no? A DC voltage V in. We added this to the input signal, the signal we wish to amplify, to prevent the output from being distorted. This is what we call the bias voltage. So, remember, no? This is the signal we want to amplify. We had to add a DC component. Okay? This DC component, we call that your bias voltage. So this now, plus minus, this is now V capital I, capital N. Remember when we discussed the convention for variables and subscripts? Okay. When you say small v, capital I, capital N, that means it is time varying. Okay. Composed of a time varying component and a DC component. No? So graphically, this is how you can show it. This is your total signal, small v, capital I, capital N. You have your time varying component, small v, small I, small n, and then you have your, we call this your bias voltage, which is V in. So this is what shifts your signal upward. It has to shift upward so that even in the absence of an input signal, even in the absence of V in, your transistor is still operating in active mode. So that's what this bias voltage does. So remember the first demo I showed you with my simulator, when I removed this, okay, my transistor was not operating in active mode all the time with just this signal being applied. Okay. And this has to be properly selected. Why should this be properly selected? Because we want to maximize the peak-to-peak value of the input signal that can be amplified without distortion. We want to maximize the peak-to-peak value of the input signal that can be amplified without distortion. That's why we have to select the bias voltage properly. And that way, we also maximize our output voltage swing. So that is what biasing is all about. In the next lecture, we're going to be talking about biasing. Okay, what are the biasing challenges? What are the biasing challenges? Number one, we don't want to have to provide a DC source for each signal we want to amplify. So remember, no, we want to amplify this signal so that this is placed in active mode all the time. We have to provide this DC source. Now we don't want to have to do that for all signals we want to amplify. No? So for example, if I had a multiple input signal circuit, no? Input circuit, I would have to provide the same number of DC signals to properly bias all of these input transistors. No? So that's the first challenge. Second challenge is we want the operating point of the amplifier to be stable. I'm going to discuss that later on when we discuss biasing. No? And then the third challenge is we need a way of coupling the input signal to the amplifier input. Okay, this is not obvious yet now, no? Why this is a problem. It's going to be obvious later on when we see the different methods that we're going to be using in biasing a transistor. Okay, so this is part 2A. No? Hanggang dito lang. So the next lecture, which I want to start already, is about biasing. We're going to jump into biasing. So before I go on with the next topic, or rather with the next lecture, are there any questions? Any questions? You can either shout out your question or input it into the chat box, where I can see it. Kung nahihiya kayong magsalita. Oh, okay. Somebody's asking what simulator I used earlier. It's a very simple simulator. It's called uh ano nga ba pangalan niya? Every Circuit. No? It's called Every Circuit. I think they have a free version. No? Of course, I'm not using the free version, but I think they have a free version which you can use. Any other question? Okay, so the question is, how come the gain increases when we decrease R's of B? No? So let me go back to the circuit of my amplifier. Okay. Okay. If I decrease RB, what will happen to IB? Will it increase or will it decrease? Okay. Can you answer me, Sarah? If I decrease RB, what will happen to IB? Will it increase or will it decrease? Yes, it will increase, no? If I decrease RB by this formula, IB will increase, no? If IB increases, obviously IC will also increase, right? Okay, if IC increases, then the voltage drop across RC will also increase. And therefore, your output will change more, no? The change in your output will be greater. Okay, so the change in your output is greater, then your gain is greater. So that's what happens, no? That's what happens when you decrease RB, your gain will increase, no? Another way of increasing your gain, it's not obvious from this discussion, is by increasing RC. No? So you can increase your gain by decreasing RB. You can increase your gain by increasing RC. Because if you increase RC, for the same amount of IB, you have a greater voltage drop here, and therefore your output will change more. So that is also one way of increasing your gain. Okay, I hope I answered that question. Any other question? Okay. Yeah, no, you have to think of gain as the change, no, as the change, not the absolute value. Okay, any other question? Okay, so if you will allow me, I will just get the next lecture started. No, I'm not going to finish it. I don't want to overload you. So let's just get the next topic started. So parang patikim lang, no? Okay, so we will discuss BJT biasing. BJT amplifier biasing. Okay, so this is what we're going to discuss now, biasing basics. I already gave you an introduction of what biasing is all about. No? Biasing is providing the DC offset voltage to your input to ensure that your transistor will always be operating in active mode. No? But much more than that. No? Much more than that. No? It has to be selected properly so that you maximize the input voltage that can be amplified. No? The amplitude of the input voltage that can be amplified without distortion. So the first biasing scheme that we're going to take up is what we call the fixed bias circuit. And then I'm going to introduce bias stability, and then we will stop there, and then we will continue next time. So I don't think we're going to go all the way to 4 o'clock today. Okay, so let us review again what I mentioned just earlier today. Biasing basics. First of all, let me define what we call the operating point of an amplifier. The operating point of an amplifier. We also call this the quiescent point or the Q point of an amplifier. This is the state of the amplifier at zero input signal. Okay, so this is from the previous lecture just a while ago. No? This was the circuit that we had. So we had a DC offset voltage. We had the signal we wanted to amplify. The total of these two, we call it small v capital IN. Okay. And then we had this transfer characteristic curve. What is our operating point? The operating point, also called the quiescent point, also called the Q point, is the state of the amplifier at zero input signal. So what is the state of the amplifier when this is zero? No? When this is zero, my base current is 0.94 minus 0.7 divided by 10K. No? 0.94 minus 0.7. So I'm again using the simplified model of this transistor. The simplified model of this transistor is from base to emitter, this is just 0.7 if it is conducting again. No? So when this is 0, 0.94 minus 0.7 is 0.24 divided by 10K, that is 24 microamperes. Okay. If I multiply that by beta, beta here is 100, that's 2.4 MA. Okay, 2.4 MA. So what is my output? My output is 5 minus 2.4 MA times 1K, which is 2.4 volts. So 5 minus 2.4 volts will give me 2.6 volts. I call that my Q point. 2.6 volts, 0.94 input, 2.6 volts output. That is my Q point. The output when V in is equal to 0. Okay, let's talk about what we call the load line. The load line. The load line is the plot of the line that is formed when you apply KVL to the collector circuit. So if I apply KVL to the collector circuit, what is KVL here? VCC minus ICRC, no, is equal to VCE. No? VCC minus ICRC is equal to VCE. No? So you might think of it this way: VCC minus VCE is equal to IC times RC. So that is this equation. VCE is equal to VCC minus RC IC. That is what we call our load line equation. The premise of that is RC is the load, no? So you might think of this okay? So think of this as the load, no? As the load of our amplifier. If I plot that, IC versus VCE, it is just a straight line, no? With a negative slope. When IC is equal to when VCE is equal to 0, so this is VCE, no? When VCE is equal to 0, then we see that IC is just VCC over RC, no? So when this is equal to 0, I compute for IC, that's just VCC over RC. On the other hand, when IC is equal to 0, so that's this point here, IC equal to 0, my output, VCE, will just be equal to VCC. So that is your load line. Okay, at the Q point, so how do we compute for the Q point? We say that Vin is equal to 0. So what is IB? If this is equal to 0, that's just V bias minus VBE over RB. And I will append to the subscript Q just to indicate that this is the quiescent base current IBQ. V bias minus VBE over RB. That is my quiescent base current. Okay, so that is going to be one of these curves. So remember, these are your characteristic curves of your transistor. We discussed characteristic curves the last time. No? These are the characteristic curve. Each value of IB will have one particular characteristic curve. No? So let's assume that this quiescent base current is one of these. It's one of these. As a matter of fact, let's assume that it is this, IB2. So pagpalagay na natin, yung quiescent base current nagkataon is IB2. What is your operating point now? Your operating point will be the intersection of this curve and of this line. That is going to be operating point, no? The intersection of this line, your load line, and this particular curve corresponding to your quiescent base current. So this is your operating point. No? Of course, your operating point will have a corresponding value of IC and a corresponding value of VCE. No? The value of IC will just be beta times IBQ, so that is going to be ICQ. Whatever IB you get here, you multiply by beta, that will be ICQ, no? That will be ICQ, beta IBQ. And of course, you have a VCEQ. What is VCEQ? This is just going to be VCC minus ICQ times RC. No? VCC minus ICQ times RC will just give you VCEQ. V out is going to be VCEQ. No? By the way, no, VCE and V out are the same. Okay, so now let's imagine applying our input. So we know now our operating point. Let's imagine applying our input. If my input is positive, what will happen? No? My input is positive, my base current will increase. No? So maybe from this base current, I'm going to be now at this base current. No? So if I'm now at this base current, my transistor will now be operating at this point. No? So when my input is positive, okay, so this is increasing V in, my transistor will now be operating along this line in the upward toward the left direction. So my output will actually be decreasing. My collector current will be increasing, but my output will be decreasing. On the other hand, when my input is decreasing, well, obviously it's going to be now going here in the opposite direction. No? So this is decreasing V in. Okay. Now, what is your output voltage swing? Okay, your output voltage swing, remember, you want to avoid distortion. To avoid distortion, your transistor always has to be in the active region. So here, it stops being in the active region here. Here, you're already in saturation. And then here, you are in cutoff. So this is your active region. Okay, so this is your output voltage swing. Okay, so you notice that if you want to amplify a symmetrical input signal, okay, that is, you want it to be able to go up and go down the same value, then you choose a Q point that is somewhere in the middle of this voltage range. No? So it looks like this is a pretty good Q point. No? It could be better, but it looks like this Q point is not bad at all. No? It is somewhere in the middle of this point and this point. Are there any questions? Any questions so far? Okay, so biasing considerations. I already mentioned this earlier. No? Number one, no? The Q point must allow the input to be amplified without distortion while allowing the maximum possible output voltage swing. Okay, I think I've been stressing that already for the past I don't know how many minutes. No, proper choice of the Q point, which is established by your V bias, no, or your V in, the DC component of your input signal. Number two, I also mentioned this already earlier. It is not practical to establish the Q point by placing a voltage source in series with the input signal. No? Otherwise, if you have 10 inputs to your circuit, you would have 10 voltage sources. No? So that is not practical. No? Or if you, yeah. Okay. So how do we want to be able to bias a transistor? We want to be able to provide the bias from the main power supply. So usually your circuit will have a main power supply, and you want to be able to derive the bias from your main power supply. And we usually do this, not usually, no, we do this, always do this, through a resistive network. I'm going to give you a very simple example in the next slide. Now, the third biasing consideration is the Q point must be stable. So it's going to be premature for me to talk about this now. We're going to talk about this more in the later part of this particular lecture. Okay, this is what we call the fixed bias circuit. This is the simplest biasing scheme that you can have. the simplest biasing scheme you can have. So here we're only talking about providing the bias, providing the offset voltage to your input. Okay, so what did we do? From your supply voltage, we have a base resistance connected to your base. And this is now used to establish the base current of the transistor at zero input signal. Where's our input? I'm not showing you the input signal yet, no? But this is what is used to establish the base current of the transistor at zero input signal. So we might say that IBQ, no? IBQ now is this current, the quiescent base current is VCC minus VBE divided by RB. Okay. Now, for Q-point calculations, it is often sufficient to just use the constant voltage drop model of the BE diode. No? So what is that? No? If this is silicon, then we just say that this, no, is 0.7 volts. No? That's the constant voltage drop model of the BE diode. This is for Q-point calculations or for DC calculations. Because if you wanted to be more precise, you could have used the Shockley model or the exponential model of this particular diode. But we already know that when you use the exponential model, you would have to resort to iteration, or you would have to use the special functions of your calculator to be able to solve the value of IBQ. So we want life to be simpler. After all, this is just a DC calculation. So usually, yeah, 0.7 na lang. No? Ginagamit na lang natin yung VBE equal to VBE active, which is approximately equal to 0.7 volts. Okay, so let's go ahead with our Q-point calculation. So actually, this is repeated here, no? IBQ is VCC minus VBE over RB, okay? So here, VCC and RB fix the value of IBQ, no? So we assume that VBE, so here we assume that VBE is approximately equal to a constant. No? So example, 0.7 volts for silicon. No? So if this is constant, IBQ is established only by VCC and by RB and nothing else. ICQ is just beta times IBQ. So in addition to VCC and RB, what establishes ICQ will be beta. No? So IBQ and beta dictate the value of ICQ. Again, no? IBQ is dictated by VCC and RB. And finally, the quiescent value of your output, in this particular case, VCEQ, will just be VCC minus ICQ RC. No? So that's the only time RC comes into play. That's the only time your collector resistance comes into play. Now, this is important because VCEQ is important because that is what will establish what your maximum output voltage swing will be. We said that you should try to position VCEQ as much as possible in the middle of your linear operating range. In the middle of your linear operating range. Okay, so this is the biasing scheme. We call it a fixed bias. The reason why we call it a fixed bias is because IBQ is fixed by VCC and RB. In other words, once you place RB there and once you establish VCC, okay, hindi na magbabago tong IBQ na. Yeah, it is fixed, no? Okay, and then because beta is also a constant, ICQ is also fixed. And therefore, VCEQ will also be fixed. That's why you call it a fixed bias. No? Once you put in the components, you already fix your Q point. Okay, what is the effect of varying RB? What is the effect of varying RB? So remember what he said? The smaller the value of RB, the greater the value of IBQ. No? So this would have a smaller RB. No? This would have the largest RB. Largest RB would result in the smallest IBQ. No? Next largest RB. Okay, so slightly larger RBQ and so forth. No? Then this is an even smaller RB, which will result in the largest IBQ. No? So showing here RB1 greater than RB2 greater than RB3. Pag malaki yung RB, maliit. No? Pag maliit yung RB, malaki. So if we chose this as our quiescent IBQ, my Q point will be here. If I chose this as my quiescent IBQ, my Q point will be here. About this, my Q point will be here. So obviously, this is a better Q point than this or this. Ano? So Q2, by inspection, is a better Q point than Q1 or Q3. So that is the effect of varying RB. Okay, so remember that when you hit this point, that is saturation. When you hit this point, that's cut off. Okay, so your maximum output voltage swing would be VCC minus VCE sat. Okay, what about varying VCC? What is the effect of varying VCC? Let's go back to our circuit. So what's the effect of varying this? Okay, so if I increase VCC, I obviously will increase the value of IC. No? So this is the largest value of VCC, the next largest value of VCC, and this is the smallest value of VCC. No? So when this is my VCC, my load line is going to look this way. When this is my VCC, my load line is going to look this way, and so forth. No? Now, when we increase VCC, we also inadvertently increase IB. So when I increase VCC, because of this loop, I increase this, I will also increase IB. Okay, so that's what it's showing here. No? If, for example, if this is my original Q point, I decrease VCC, no, my IB will decrease. If this is my original Q point, I increase VCC, my IB will increase. Okay. So again, no, itong Q2 would probably be a better Q point than Q3. No, so in choosing VCC, this might be a better choice for VCC than this or this. You know? So this looks like a better VCC. And then finally, what about RC? What is the effect of RC on the Q point? First of all, note that RC is not going to affect the value of IBQ, no? For as long as your transistor is in the active mode. RC, this has no effect on IBQ. Okay. What will happen if I increase RC? Okay, if I increase RC, my IC will decrease. Right? My IC will decrease. No? If I decrease RC, my IC will increase. So this is the smallest value of RC. Okay. the next, and the next. No, this is the next. Okay. So that is the effect of RC on the Q point. Okay. Okay. Next is applying the input signal. So we only talked here about the biasing circuit. No? How do we apply the input signal? The input signal is capacitively coupled. So this is how you apply the input signal. You apply it through a capacitor. What is the characteristic of a capacitor that makes it possible to do this? It acts like an open circuit to DC. Therefore, this will not affect the DC currents that flow here. No? Okay. Vin will not affect how the transistor is biased. On the other hand, VCC will not find its way into Vin and will not influence Vin. No? So because of this capacitor, with respect to DC, Vin and VCC are disconnected. VCC will only establish the bias here. C must be sufficiently large so that at the input frequencies of Vin, it approximates a short circuit. No? So what is VCE? VCE will be the sum of the contributions of VCC and Vin when each is considered acting alone. So you recognize that. No? That's something like superposition. If you consider VCC acting alone, that is just the biasing. If you consider Vin acting alone, that is the time varying component of your input. So if you take both of these into consideration, you just add the responses, you're going to have an output that has both a DC component and a time varying component. The DC component is established by VCC. The time varying component is established by Vin. And when Vin is considered acting alone, that's what we call small signal analysis. And this ends up being applied directly to the input of directly to the base emitter junction of your transistor. Okay, I'm going to stop here, no? Because I think that's already a lot. No? I will probably re-emphasize some parts of this discussion when we meet again on Thursday. Are there any questions? No questions? Maybe none yet. Let's see. Okay, thank you for the response, Cheska. Okay, so I'll give you time probably to absorb this lecture. I'll be posting the recording, and I'll clean up a little bit the annotation so that it's a little bit clearer. And then we will continue with this on Thursday. No, I will close the session when the last of you leave, so that if there's anyone that wants to ask any question whatsoever, I will still be around. Okay, that's it.